approximate full slipping, you can see the. Of course, you are not in normal coordinates, so you do not see the curve from above, the helix. You see it with some perspective, but you imagine that if you look it in the good perspective, it will give you the elastica. Okay, this was then second one, the ball with the trailer. Okay. So now, again, you see it from some perspective, not from above in normal coordinate, and you see that you move, you see this hyperelliptic curve. Let me continue to say that. André suggested that a hyperelliptic curve is not a good denomination, that better would be hyperelastica, because in fact the elliptic curve is not the curve in xy. It is the curve before you integrate, and for elastica it is the same. Then in a sense it is a hyperelastica. I agree with him. Okay, so now I go to the Gursa case. And for Gursa case I have slides, but I am not responsible for these slides. They were made by my co-author, and when preparing my talk, I realized that there are some mistakes, not to say a lot of mistakes. I will not tell you where they are, but if you see, I am not responsible for them. Felipe Monroy is. Okay, so there is something that I shall skip immediately. Generality, definition of this entropy again, and okay. I recall that these results. This is interesting, but they are not. It is another paper a recent paper that I have with Matiaskowski, which is a completely different point of view. Now I pass to Gursa distribution. So distribution is Gursa. If it is like that, you have these two flags attached to the distribution that are the same and that grow by step one at each step. So we have this property, and you have this theorem which claims that there is these von Weber coordinates are very, very interesting. This guy this theorem is from 1898. And these coordinates are the von Weber coordinates. It is coordinates that the engineers call the power coordinates. But in fact, it is von Weber coordinates. They are due to him. And up to local diffeomorphism, you can always put Gursa under this normal form. There is a unite. So I call it the von Weber normal form and the von Weber coordinates. And of course, now, just in this case, I will forget about the normal coordinates and work in the von Weber coordinates, because for this problem they are very, very natural. Okay. So you two vector fields. The two vector fields are x1, x2. X1 is just ddx1, x2, and I define the vector field xi, which is which successive left brackets by x1. Okay. So now there is a problem of parallel parking of a car. So you have a car with n trailers, and it is Gursa distribution. This has been shown first by two guys, Murray and his student Tilbury, female student as far as I remember. They have proven this. It means what? It means that if you take the equation of the car with several trailers is quite simple. It is easy to understand. Okay, you have the car which is x dot equals cosine theta u, y dot equals sine theta v, the same u, and theta dot equals v. With v you turn, and with u you go straight here, and you attach. If you attach a trailer, a first trailer, so you have phi 1 dot, which is a certain function of previous variables, phi 2 dot, which is certain function of previous variable, and the phi are the successive angles with which you attach of the trailer. They proved, these guys, that in fact car with a trailer is Gaussian distribution. Of course, there are some assumptions on the length of where it is attached and so on, but let me forget about that. And then it is very interesting from engineering point of view, because it means that you can find the feedback and the change of coordinate such that not only your nilpotent approximation is under Gaussian normal form, but the car with a trailer itself, which it is very important property from practical point of view, because it's what it says. It says that if you do like that, the epsilon of the interpolation entropy has not to be small. Your system is exactly because, as you can see, von Weber form is its own nilpotent approximation. Of course, you read it immediately on the form of the vector field. It is its own nilpotent approximation. So by feedback, you can reduce to the nilpotent approximation of the system, and then the story of interpolation entropy becomes completely exact. But this is provided, it is a bit crazy, because this is provided that you choose as the metric the sum u1 square plus u2 square that corresponds to the feedback which is necessary to go to von Weber form. Then you do not know what you minimize, in fact. What you minimize is determined by the feedback that you need to go to von Weber coordinates. But from practical point of view, people do not care much about what they minimize. Their main problem is to minimize something. Okay? So it is like that, but it is quite important. Then, okay, I explain this. There is the story of nilpotent. So nilpotent approximation is nilpotent approximation. So it is the same in von Weber coordinates. So let me jump. Here I gave the proof, the general proof of the fact that in this problem of interpolation entropy you can restrict to nilpotent approximation, but this is not too important in that case. And this is what I just said. There are two things. If you are given a metric, you want to minimize this metric, you have to go to nilpotent approximation. If you don't care about what you minimize, which is in general the case for engineers, you go to von Weber form and you minimize the corresponding, you consider the corresponding Sub-Riemannian metric. In the first case, what I say is true for large epsilon. In the case where you have the von Weber metric, but if the metric is given, of course, what I say is still true only for small epsilon. Here is the trick. So nilpotent approximation and small epsilon or not, depending on the fact that you are given or not, that the metric you are given is different or equal to the van Weber metric. Okay. Then these two vector fields, they generate the Gursa Lie algebra, and you have the Gursa group, which is simply unique, simply connected group, nilpotent corresponding to this Lie algebra. Then it must be on Rn. And in the van Weber coordinates, the group law is very simple. It is just like that. Okay. And of course, our two vector fields are left invariant vector field with respect to this group structure. Okay. This I don't care. Okay, so now as usual we apply minimum maximum principle, and my coauthor does a lot of calculations to check that this guy is Liouville integrable. But there is not any there is not any computation to do. You have no computation to do to claim that it is Liouville integrable, because there is one single variable appears in van Weber coordinates. Then all components of a joint vector are constants of the motion plus the Hamiltonian, which gives you exactly half commuting half of the which gives you exactly L, so half of the dimension of the Hamiltonian system, commuting first integrals. Then it is clear that from the very beginning that it is integrable. Nevertheless, it is always interesting to this. What it does is not completely stupid, because it is always interesting to understand the thing in a more intrinsic way. And of course, the interesting guys are these Hamiltonians, corresponding to all these vector fields that are the first vector field bracketed with the second from the left. So what you get, in fact, you get the following. You get that, of course, so I call this guy Hi. I remind you that xi plus 1 is ddx1, x1, which is ddx1, times xi minus 1. It is like that. And pxi is the Hamiltonian Hi, and h, the full Hamiltonian of the system, is as usual 1/2 h1 square plus h2 square, and as usual I consider the level 1/2 of the Hamiltonian for the things we parameterize by arc length. And then you get to the for the geodesics, you get to this very interesting story. Hn minus 1 is a polynomial, sorry, excuse me, H2 is a polynomial in H minus 1. On the other hand, Hn minus 1, for the reason, the same reason as usual when you differentiate in nilpotent Lie algebra, at some point you go to 0. Hn minus 1 is something linear in X. So Hn minus 1 is Cx plus D. It is a fine function of X. So this expression is very interesting because of this. On the one hand, you have the cylinder h1 square plus h2 square, which is motion is on this, and you have H2, which is as I've shown, H2 is a polynomial in Hn minus 1. So if you look in the three coordinates, if you look in the three coordinates, H1, H2, Hn minus 1, you get this picture. You have on first cylinder, basis of which is a circle, H1 square plus H2 square equals 1, and second cylinder, it is a cylinder in the direction of H2 with the basis is the polynomial, this polynomial. And then integral curve in the coordinates H1, H2, Hn minus 1 are these hyperelliptic curves. Okay? If you look at them from above with the Monroy, so they are like that. Then we call them the cacahuète. It is reasonable to call this guy cacahuète. Yes. Because the second one, this is a cacahuète, a peanut, no? You don't agree? It's not a peanut? Okay. So we call them the peanuts, and so these are the curves that you have to integrate to get the motion. This is the story. But so, how much time? How
15 minutes. 15 minutes.
15, okay, it will be okay. Because there are many things that I will not say. But okay. I went to the problem of the parking of the car with the trailers, of course. It is exactly the case where you are so you want to go in the direction of the last bracket. So you want to park like that, a car with several trailers, you want to park it here. And so now, okay, clearly X, Y are the positions of the car on the plane, and the following are the angles. Then in following are homogeneous two angles. They are not exactly these angles, but they are angles. And okay. And then okay. X, by the way, not X and Y both are hyperelliptic, but X at least is. Why? Why? Because Hn minus 1 is in fact X. Then for that reason, Y is not hyperelliptic, but X is. And X is given by this formula for a certain polynomial. So it is of this form. The solution of this X is given by this hyperelliptic integral. And then we compute this, and okay. I don't know if I give details, but coefficients of this free polynomial, of this polynomial, H2, which is a function of Hn minus 1, determine everything. Okay? So there is a certain number of clear symmetries in the problem. The clear symmetry is that you are symmetric with respect to the x. There is clear symmetry with respect to
So
the...
your goal is to find the projection such that all coordinates but the last one are periodic.
Yes, but the last one
that's the
are
goal
periodic.
if you want to parallel
Yes,
parallel.
in fact you can interpret it like that. You want to find a closed curve on the plane such that it is periodic, of course. The area is 0, A area. This is the fact that the bracket produces the area of the curve. Area A of the curve is 0, but A, you have the area swept by the curve. It is a variable along the area swept by the curve is a function of the coordinate on the curve, A of t, and you want that all the moments sum over the curve c of x power I dA are 0. You want the area to be 0 and all these moments to be 0 except the last one that has, on the contrary, to be maximum. It is what you want, exactly. The problem is equivalent to this. Finding a closed curve such that the area is 0 and all these moments are 0 up to the last one, which is itself maximum. It is what this problem solves. Then there are clear symmetries in the problem. You have one symmetry which is clear. It is a symmetry with respect to the x in the problem. But the symmetry with respect to the y is not so clear. There is little difficulty. The set of solutions is symmetric again. But who knows if the all solutions themselves are symmetric? Then, and this I don't know, we assume that the solutions actually themselves are symmetric. But there is a very well-known problem, the Newton's aerodynamic problem, where such assumption was made and by Newton. And it is false. And the set of solutions has this symmetry property, but recently it was shown that the solution, that there are several solutions and that are actually not symmetric. Then up to this, I assume the missing symmetry with respect to the x-axis. Then in this case, what you have that. So the only data in this problem is the coefficients of this polynomial, pk. But due to these symmetries, if you center to the center of symmetry, there is automatically half of these moments that are 0, automatically, just due to the symmetry. And then, with the number of coefficients that remains, is exactly the number that you need to vanish the moments and to make y periodic, of course. We know that x is periodic hyperelliptic. Then you have exactly number of parameters that is needed to get to satisfy the interpolation conditions. It is why I think that it will certainly not be the case in general situation, because you have much more, because at the end the picture is like that, okay? If you compute this hyperelliptic curve, then you get these motions. It has been computed for 6 n equals 6 and 7, then 3 and 4 trailer, So here are the cacahuètes, and here are the optimal hyperelastic car. You can see that the case, odd even case, are quite different because in one situation the symmetry, the center of symmetry is on the curve. In the other situation, it is not. It makes some little difference to compute the guy, but you get that. And to finish, so question, several questions. So find, show that actually the solutions are symmetric, because this is missing. Nevertheless, we get. Maybe we do not find optimal trajectory, but we find extremals that meet the interpolation conditions and that have the required number of loops. Then I would be really surprised if they are not optimal. But the theorem that I claim is just that they are extremals, meeting the transversality conditions. So prove this. And what I really think is that, in fact, in the general case, for this reason, that you here, each time you grow the non-autonomy degree of 1.
General, you mean not Gaussier?
Not Gaussier. Then here you have exactly number of coefficients needed for Gaussier, in a sense. Then my conjecture is like that. It is the following. And it is related to the end of my of the previous half of the talk, where I had things to say that go also in this direction. But my conjecture is now the following. It is that in general you have a flower like that. Optimal trajectory should be a flower like that, and in that case it is a flower with only 2 petals in Gaussier case. You have a flower where number of holes is half of the non-autonomy degree on each petal, but the number of petals is related to the dimension of the component of the homogeneous component of the last homogeneous component, the last of the free nilpotent Lie algebra that is concerned in this problem. This is my conjecture now. I changed the conjecture. It is like that. You have a flower with a certain number of petals. Number of holes in the petals is half the non-autonomy degree. Okay. And this number in the Gaussier case is 2. And number of petals is related, I don't know how, with the dimension of the homogeneous, of the last homogeneous component of the free Lie algebra that you are concerned with. This. I finish with this, and I show you again maybe the race, the race that I showed you. It is the race between a classical method to solve this parking problem and my method. Here it is. So I am on the left, and the classical method is on the right, and when it stopped, I am arrived at the. Well, okay, I already arrived. Some comments maybe. The curves that you see on the ground, curves that correspond to the motion of the car, they have cusp. Of course, they must have cusp. If you park a car, you must have cusp. But it is a bit surprising, cusp. But this is due Legendrian singularity. If you project in some direction in the ball,
It is projection.
it is quite but you project from. But
perfectly smooth. What projection has?
No, but look, when you look at the ball with a trailer on the other, you project from something. You do not get cusp. Okay? Here you project from Legendrian. Then you have Legendrian singularity. It is why you get cusp. In that case. Okay, maybe. Okay, I finished. Yes.
Two questions. I'll start from the last. First, I would like to ask about integrability that you showed. Can you say again how did you what are first integrals? So you have the Hamiltonians and the rest n minus
You
1.
have this hn minus 1 and you have other, but once you have these three, you get everything in coordinates easily.
No.
There are certain polynomials in the H1, but in coordinates, the first integrals are the Hamiltonian and P2 to Pn, because Hamiltonian depends only on the first variable. Then it is clearly Liouville integrable, because these Hamiltonians clearly commute and you have the required number. So these are the constants of the motion.
And P1 it's H.
In
no?
coordinates.
It's H capital.
No, now after I prefer to...
Because Hamiltonians depend on H1 and
H1, H1 is P ddx, so it is P times X1, so actually it is P1. Yes.
Okay, and
But H, I did not say that H1 is first integral. I say that P2 to P6 are first integrals, and the Hamiltonian itself, H1 square plus H2 square, are first integral.
Yeah, but he probably interested in the action coordinates. So some combination of this Hamiltonian that...
Yes, so they are. It is like that at Monroe. So some combinations, some polynomials in this H1, H2. This is detailed in the paper. They are computed. The constant of the motions are computed in terms of the H1, Hi in the paper.
but it is already obvious that they are functionally independent, yeah?
Yes.
So this is the first question. Yeah, thanks.
Yeah, no, but it is clear. Liouville integrability in itself is clear in coordinates.
The rest is just to find
Immediate.
action angle. Yes.
In coordinates, the technical maybe. I don't know if it's true or not that when you consider the system with Grove vector 2, 3, 5, 6, so you
It is different. It is not Bursa.
No, it's not Bursa.
But 2, 3, 5, 6 is integrable in a completely different way. It is much more complicated. I just gave idea of why it is integrable.
But there is also integrability, yeah?
There is, of course, integrability.
There
is integrability. There is integrability in the case of the car with of the ball with the trailer, which is a case where the invariance, the ratio of the eigenvalues, is equal to 1. In other cases, I think that it is not integrable. But of course, I cannot prove, because it is always, as you know, almost impossible to prove non-integrability.
So in this system car,
ball
with a trailer, I think it is also possible to see on this, to look at this as a car with 3 trailers. But when they fixed in different...
maybe, yes.
I think maybe even for...
But the car with 3 trailer, why the invariant will be precisely, the ratio of eigenvalues will be precisely equal to 1.
Brackets are different. It's 2, 3, 5, 6. It's not Bursa.
No, I mean if to fix the trailers in different way. Like 2, 3,
Yeah.
5, we add one more trailer and we have 2, 3, 5, 6, I guess.
Yes, you have 2, 3, 5, 6, but you certainly have to. But you certainly have 2, 3, 5, 6. Probably have 2, 3, 5, 6 non-integrable. I started a study with a student of mine of a general case, but when the ratio is close to 1. Because it is a story of perturbation of integrable Hamiltonian, you have CAM and so on, and you can expect that these many properties of these periodic trajectories are preserved. But I don't see another way I cannot prove integrability, and I don't see another way to tackle the general problem. Well,
Thanks.
And do you have an example of a controllable system with flower, with some?
no. Clearly, no. I have no example up to now.
But some
This flower is a flower that is not that is not optimal. It is the optimal one in that case. It is not optimal for this problem. It is certainly optimal for a problem with other initial and terminal conditions. But it is a geodesic which is periodic and which satisfies also the interpolation conditions, but that's it. In fact, in the case of the ball with a trailer, to integrate this Hamiltonian, you have to make appear another Hamiltonian, which is simpler, which you can explicitly integrate, and the period of the first one is integer multiple of the period of the one you can study. And this period again, you prove that it is not one, and you find a geodesic with two. Then it is a flower with two loops, with a half of. But also the example in dimension, the case of the elastica. Elastica is optimal. You clearly see that it is a question of number of boundary conditions. Elastica is optimal for 2, 3, 4 case. Whatever the point you start on it. It is optimal in 2, 3, 5 case, the presence that nature gives you, but only if you start from a precise point on it, the singularity. Then this means that you use special point to satisfy the second interpolation condition in that case. It goes also in the direction that when it grows, when number of brackets grow, you will not have enough coefficients to satisfy the boundary conditions. It goes in the same direction. For all these reasons, I think that if there is a result, it is like that. This flower, and I think that the size of the flower is half of the non-holonomy degree, and number of petals is related to the number of brackets you have, to the number of brackets you have. In fact, maximum will be for the free nilpotently algebra, so it is related to this universal number.
Is it all? Oh, yes, you should.
After all.
In this case, for this course of lectures.
I hope